Hi, I'm Tiffany.
I'm Madeline.
And I'm Nathan.
And today we are going to talk about gravity and its relation to our planet. Ever wondered why we don't float on Earth like we would on the moon? Probably not, but we're going to tell you anyways. It's this funny thing we like to call gravity. Several years ago in a galaxy far, far away, just kidding. This cool guy named Isaac Newton discovered the gravitational constant that will be featured later today. Today, we're going to be focusing on the equation for gravitational acceleration. The gravity of the planet is equal to g, the gravitational constant, times the mass of the planet over the radius of the planet squared. Which is a mouthful, I know, but we'll come back to it later. Before that, we want to give you a flashback to your childhood to give a little bit more insight on this topic. Hit the clip.
Come along, class.
Hey, I feel like I weigh the same here as I do on Earth.
That's because Venus is about the same size as Earth and has about the same gravity.
Come on, Arnold.
Now you're probably wondering, so what? Well, I'm afraid to say that Miss Frizzle lied to you. Shocking, I know. The truth is that the gravitational acceleration of a planet is actually caused by the mass of the planet, not the size as stated in the clip. We can prove this using the equation for gravitational acceleration, little g equals big G times mass over radius squared, where little g is the gravitational acceleration of our planet and big G is the universal gravitational constant, 6.67 times 10 to the negative 11th newtons, or kilograms times mass per second squared. To give an example of this, we will solve for the gravitational acceleration of Earth. If we take big G, 6.67 times 10 to the negative 11th newtons, times the mass of Earth, 5.9724 times 10 to the 24th kilograms, over the radius, 6,387,000 meters squared, comes out to 9.8 meters per second squared. We can now compare this to Venus by taking big G, 6.67 times 10 to the negative 11th newtons, times the mass of Venus, 4.868 times 10 to the 24th kilograms, over the radius, 6,052,000 meters squared, which comes out to 8.87 meters per second squared, which gives us a difference of approximately 1 meter per second squared. This difference would be nearly unnoticeable to humans walking on Venus. Now, while this may seem accurate to the clip we watched, it is only by coincidence that Venus is also similar in size to Earth, because the mass of a planet is not caused by its size.
So, in conclusion, the gravitational acceleration on each planet depends on its mass and radius. Although it would be easy to assume that walking on a planet would be the same anywhere in the universe, these two factors can completely change the way that gravity works. Whether you're walking on Earth or jumping on the moon, gravity plays a major role in every step you take. How cool is that? Of course, with this knowledge of gravity, we don't want to mislead you with the hypothetical scenario of walking on other planets in our solar system. Just like there are many factors that contribute to gravity, there are also hundreds of other factors that go into realistically visiting a planet. For example, on Venus, the average temperature is about 430 degrees Celsius. This temperature alone prevents any human from even thinking about traveling to that planet. So remember, although hypothetically walking on Venus would be similar to Earth, I do not recommend visiting.
Well guys, I'm Tiffany.
I'm Madeline.
And I'm Nathan.
Thank you so much for hanging out with us. We hope you enjoyed learning about gravity just as much as we did. Have a great science-filled rest of your day.
Planet, sorry.
That's for sure. You're good. Miss... Stop staring at me!
Times the mass of the planet's...
Wait for the door to slam behind you. Don't let it hit you on the way out.
Hey. You know what makes my blood boil? Venus!